Good day and welcome back to the second installment of our discussion on continuity. In the previous video, we introduced the concept of what it means for a function to be continuous at a point, and then we investigated the consequences of that definition from both a graphical and an analytic perspective with a few concrete examples. In this video, I'd like to kind of step it back to the big picture perspective and just think about the fact of how we can maybe combine continuous functions to form more continuous functions, and kind of also what are the common functions we've encountered in the past, say in pre-calculus, that we now know or are guaranteed will be continuous wherever they are defined. So the reminder, we say that a function f is continuous at x equals a if the limit as x approaches a of the function is equal to the function value f of a. And remember, this very simple, innocent looking statement involves three key things that must be true. The function value must be defined, the limit as you approach f must exist at a, and those two numeric values need to be equal to each other. So in terms of kind of some properties, if you have two functions f and g and you know they are continuous at x equals a, there are many different natural ways that we would combine those functions together. For example, we might think of f plus g or even minus g, so f plus or minus g. You might multiply the two functions together. You might take a constant multiple of the function, or you might take a quotient, f divided by g. And all four of these functions, maybe 5 if you want to count the plus and minus, will be continuous also at x equals a. With one small stipulation, we have to be careful with that quotient and throw in there as long as f over g is defined, which means g of a is not equal to 0. And something that this will maybe allow us to do kind of immediately is make some further observations. So the following functions that we are very familiar with are going to be continuous wherever they are defined. That is to say, at every number in their domain. And the first two come as no surprise as we've worked with them in the previous section. So a polynomial or a rational function. A polynomial or a rational function automatically satisfies that definition of continuity by the substitution property, which recall tells us that the limit as x approaches a of f of x is equal to f of a. And I'll ask you to think about this for a moment. From your past experience in, say, pre-calculus, what are some common functions you've encountered that you'd expect to be continuous? And a family of functions that immediately jumps out to me would be the trig functions. We work extensively with the trig functions, especially in the second half of pre-calculus. And those functions, if you picture their graphs, they're going to be continuous wherever they are defined. So cosine and sine would be continuous everywhere. And then the other four trig functions, tangent, cotangent, secant, cosecant, are going to be continuous wherever they are defined. And then similarly, some other functions that we encounter frequently would be the root functions. Most notably, think something like square root x, but there could also be cube root x, whatever root you might like. Those are continuous wherever they are defined. And it also turns out that there are more ways we could even think about combining functions together. Another such way would be a composition. And that leads us to our kind of final property before introducing a new limit law, is that if g is continuous at x equals a, and f is continuous at g of a, then f of g of x is continuous at x equals a. And that's maybe a bit more wordy than I think we really need to be. Let me just write this a bit more simply. The composition of continuous functions is continuous. And I can now note that if you have two continuous functions and if you combine them in any reasonable way where those functions are still defined, you're probably going to get back a continuous function. It's a really intuitive idea. But this does lead us to kind of a new limit law. And what I'm going to just note here is that if the function f is continuous, we can simply take the limit and pass it inside a continuous function. That is to say, we can take this limit as x approaches a, and we can move it inside a continuous function. So this would become f of the limit as x approaches a of g of x. So to kind of repeat, as long as the function f is continuous and the limit exists, it makes sense to just push that limit inside a continuous function. And we could get a bit more carried away with hypotheses, but I don't think we need to be concerned about that. And note, this is extremely familiar to some of the limit laws that we previously encountered. So just to remind you, we had the limit law that the limit as x approaches a of the square root of a function is equal to the square root of the limit. So as we mentioned on the previous page, root functions are continuous, so we'll just simply push that limit inside the continuous function. So we're just kind of making this past limit law and idea a bit more general. And let's see why this is useful. If we were previously asked to evaluate the limit as x approaches 0 of sine of x squared, we wouldn't have any old limit laws that allow us to evaluate this. But we have a new limit law. And recall the observation that we made on the previous page. Trig functions are continuous wherever they are defined. So sine, I'll just simply say is continuous. It's continuous on the entire real line. And our new limit law above tells us that if we want to evaluate the limit of a composition with that first function being continuous, we can simply pass that limit or push it through the continuous function. So this is sine of the limit as x approaches 0 of x squared. And note that that remaining limit is a simple, easy to evaluate limit for us. And we can justify it in multiple ways. The easiest way, I think, is just to note x squared is a polynomial. So by the substitution property, this becomes sine of 0 squared. But note, we also have another way of justifying this. You could also note, because f of x equals x squared is continuous, to evaluate the limit of a continuous function, you simply substitute in that value 0. So the substitution property may have been more aptly named the continuity property. And what we are left with is the sine of 0. And just take a moment and write down what numeric value that is. Hopefully you wrote down 0. And one final comment or observation I want to make more as a cautionary warning here is that whenever we are dealing with trig functions, sine, cosine, tangent, secant, doesn't matter which trig function, if it comes down to the value of the trig function at a common angle, so think 0, pi over 6, pi over 4, pi over 3, pi over 2, multiples around the unit circle, I always need you to evaluate trig functions at common angles. If you do not, you will most likely have a small point deduction associated with it. So just keep that in mind. So that finishes up the second part of our discussion. In the next video, we'll move on to a common example that typically provides a challenge for students. So stay tuned and take care.